Recording first. Last week we learned vapor cycles, and we first learned vapor cycles used in the power generation, and they are called vapor power cycles. Then we covered the section vapor refrigeration cycles. In vapor power cycles, uh, we solved examples regarding the Rankine cycles. Its name is Rankine cycles, using water as working fluid. Then we continued with the vapor cycles using refrigerants such as R134A for refrigeration purposes. This week we will continue with the cycles, but uh, this week we will be covering gas cycles, gas power cycles. The difference between the gas power cycle and the vapor cycle is that in vapor cycle, the working fluid alternates between liquid and gas, and condensation and evaporation occurs as the processes take place. However, in gas power cycles, there is no conversion from liquid to gas or gas to liquid, so the only phase is gas. Normally, gas power cycles are called internal combustion engines, even though gas turbines are separate from other internal combustion cycle engines. They are also internal combustion engines. Normally, we use the internal combustion engines to denote the engines that are used in our cars, power generation, and so forth, which are reciprocating. Reciprocating engines have pistons and cylinders, and pistons move up and down inside the cylinder to produce power, whereas gas turbines are completely different. So in this chapter, we will learn both reciprocating engines, both the diesel engine and gasoline engine. Diesel engine is compression ignition engine, gasoline engine is Otto engine. Then we will continue with the gas turbines. There are two types of internal combustion engines which are reciprocating. Reciprocating is the motion of the piston as back and forth. That's why they are called reciprocating engines. There are two types of reciprocating engines. One of them is spark ignition engine or Otto engine. The other is compression ignition engine or diesel engine. In spark ignition engines, air and fuel mixture is ignited by a spark plug. On the other hand, in a compression ignition engine, the compressed air has a high enough temperature to ignite a fuel which is uh, injected into the air. So the distinct difference between the two types of internal combustion engines is that while the spark ignition engine has a spark plug to start the ignition, in the compression ignition engine, there is no such thing as spark plug, and ignition takes place only because of the high temperature of the air, which is compressed. Normally, the spark ignition engines are used for relatively small power generations, such as lawn mowers, small generators, cars, and so forth. On the other hand, the compression ignition engines, the diesel engines, can be used for a variety of applications, starting from car engines to very large ship engines or power generation plants. They may be up to thousands of kilowatts, whereas the uh, spark ignition engine can be as small as much less than 1 kilowatt. The general construction of two types of engines are the same. So whether it's a spark ignition engine or compression ignition engine, or in other words, whether it's a Otto engine, gasoline engine, or diesel engine, the general construction is very similar. First of all, there has to be a cylinder, there has to be a piston which moves up and down inside the cylinder. There is a crank mechanism which converts the linear motion of the piston to rotary motion. And there are valves at the top of the cylinder. Some number of the valves are inlet valves, and some number of the valves are exhaust valves. There can be one inlet, one exhaust, or two inlet, two exhaust. It depends on the design of the engine. Differently, the gasoline engines have spark plug, which is not found in the diesel engines. We have some definitions in the reciprocating engines. First of all, the diameter of the cylinder is called bore. The distance at which the piston moves from bottom to top is called the stroke. Because the piston cannot move up to the highest level, because it cannot have a direct contact with the spark plug, or you cannot have a zero volume here, the minimum volume at the top of the piston is called the clearance volume, and the maximum distance that the piston moves is called top dead center, or just top center, and the lowest distance that the piston moves down is called bottom dead center, or just bottom center. And we have a volume, which is the minimum one, is called the clearance volume, and maximum volume is when the piston is at bottom dead center. The difference between the maximum and the clearance volume, which is the volume swept by the piston, is called displacement volume. So displacement volume is just the summation of, the total volume is just the summation of displacement volume plus the clearance volume. There is also the compression ratio, which is the volume at the bottom dead center divided by the clearance volume. So it's like the maximum volume, the total volume divided by the minimum volume. Normally, in four-stroke engines, which are found in the cars or in many applications, one power cycle is produced at every 2 revolutions. So what happens is, when the piston is at the top dead center, here, the inlet valve opens. So let's suppose that this one is inlet valve, this one is exhaust valve. Inlet valve opens when the piston is at the top dead center. As the piston goes down, because of the vacuum it creates, the air will come in. So we can see it here. This is the point, the top dead center, at which the inlet valve opened. And as the piston goes down, air is sucked in because of the vacuum it creates. So when the piston is at the bottom dead center, the cylinder is filled with air. So at this location, the inlet valve closed, and as the piston starts to move up, the air inside the cylinder is compressed. By compressing it, the pressure and the temperature will increase. And when it comes to the top dead center, or close to top dead center, then we have the ignition. Ignition is obtained by a spark plug in spark ignition engines, and by compression in compression ignition engines. So whatever the type of ignition is, after the fuel is ignited, then the temperature and pressure increases considerably so that it will push the piston down by creating power. So as the piston goes down because of the high pressure created due to the combustion of the fuel, the piston is pushed down by creating power. So when it's close to the bottom dead center, exhaust valve opens, and because there is still high pressure inside the cylinder, exhaust gases start to uh, leave the cylinder, and the rest of the exhaust gases remaining inside the cylinder is pushed out by the upper motion of the piston. So as you can see, we have a downward motion, which is one stroke, upward motion, which is a second stroke, another downward motion, third stroke, and upward stroke, a fourth stroke. As you can see, power is generated only in one stroke or one revolution. So one cycle takes place in two revolutions, and power is generated in only one revolution. There are also two-stroke engines in which power is generated at each cycle or each revolution, but we will not be covering two-stroke engines because they are mostly small engines or very large ship engines, but we will be covering only the the four-stroke engines in which the power is obtained at every two revolutions. Normally, remember that we obtain the work in a cycle, a closed system. Work is obtained as the integral of PdV over the cycle. This circle shows that the integration has been done over the cycle. And if you take an average pressure, if you assume an average pressure, it goes out of the integral so that you have a work term as work term as P average times delta V. And this P average in engine cycles is called mean effective pressure. It's an average pressure, but it's called mean effective pressure, and it can be obtained from the net work from one cycle divided by the displacement volume, which is the total difference in the cylinder volume. As you can see, as the pressure is increased or as the displacement volume is increased, there is more power generation. That's why larger engines create more power. Also, larger pressures create more power. In order to analyze the internal combustion engines, the reciprocating engines, we use two different approaches. One of them is air standard analysis. According to air standard analysis, the air inside or the gas inside the cylinder is assumed to be an ideal gas because the fraction of the fuel is much smaller than the fraction of the air. That's why we can assume that it's an air comprised of pure air. Combustion process is replaced by a heat transfer from an external source. So we assume the system to be a closed system, which is normally not, because when the valves are open and closed, and for inlet valves and for exhaust valves, when they're open and closed, there is actually mass coming inside and leaving the system, which means that it's actually an open system, but for analysis purposes, we assume the system to be uh, a closed system, meaning that we assume that there is no inlet of air or exhaust of gases so that the same working fluid is used inside the cylinder, and heat transfer is provided not only from combustion but just from some external source, and heat transfer from the exhaust system is not obtained by the rejecting of the gases or expelling of the gases. It's just cooling the gases by some external sink. The second uh, approach is cold air standard. So the first one is air standard. The second one is cold air standard. In the cold air standard, we assume that the specific heats throughout the cycles, throughout the processes are constant, so that we can use the constant specific heat approach, taking the specific heat to be the same for all the processes, even though this gives wrong results, unrealistic results. In order to analyze the system, we can use it as a starting point. On the other hand, uh, the air standard that uses the air tables, which takes into account the change in specific heat, gives you much more realistic results. So the first one is air standard Otto cycle, or spark ignition cycle, or gasoline cycle. You can call them in three names. In an air standard Otto cycle, first of all, as I had already told you, that there are no inlet of the gases or exhaust of the gases, so we have only four processes. So one process is moving of the piston up so that the gas will be compressed. Then combustion takes place in constant volume because uh, as the spark plug is operated, the ignition takes place in a very short time so that the combustion takes place in constant volume. Then, because of the pressure that has increased substantially, this pressure applies a force on the piston by moving it down, which creates the work. So this is the useful work. Then, at the end of the uh, expansion or work process, the gases are exhausted, but in this case, there is no exhaust, it's just cooling of the gases to the initial position. So we have the compression of the gases, which means we have to put some work in it. Then we add some heat, which represents the combustion heat. Then we obtain work. So this one is work in, this one is work out. And the difference between them is the net work, which is the useful work. Then a process in which the gas is cooled, which represents actually the exhaust process. This is PV diagram. And similarly, if you have the TS diagram, the compression stroke is, for ideal conditions, isentropic. Then we have a heat addition process from 2 to 3. Then we have expansion, which is the work cycle, work process in which the gases expand isentropically. Then we have the exhaust process in which gases are cooled down. Here you can see that if it's possible to increase the compression amount, so if the pressure at 2 is brought to 2 prime, then 3 prime will be larger also, because The area inside this TS diagram is the total Q, which is also equal to the total work. The TS diagram integration gives you Q net, which is equal to W net for a cycle. Then we can say that if the pressure is increased, if it's possible to increase the compression pressure, then the net area under this TS diagram is larger, meaning that we have more work, more network. The same network is actually the area under the PV diagram, because for a closed system, PDV is also another way to find the work. So the network and net area under this curve will give you the network produced by the system, which is equal to the net Q. So for a cycle, remember that because initial and the final conditions are the same, so net Q is equal to network. Now we will analyze each process. The first process is the compression work, because we assume that it takes place isentropically. When we say isentropic, so isentropic is reversible plus adiabatic. So when we say adiabatic, there is no heat interaction. So when there is no heat interaction, we write the first law of thermodynamics. So net Q minus net W is equal to delta U. For an adiabatic process, this goes away. So the compression work is just the difference of the internal energies. So the compression work is obtained from the difference of the internal work. This is the compression work. The heat added in the cycle, so heat addition takes place here from 2 to 3. As you can see here, the volume is constant. When volume is constant, because of the integral, you can see that work is 0. So when work is 0 in the heat addition, then Q is equal to delta U. So we can say that the work addition for a Otto cycle is again the difference of the internal energies. The net work of the cycle is the work during the expansion minus work during the compression, because during the compression we have to add work into the system. During the compression, the system does work on the surroundings. So the network of the cycle can be obtained from the difference of the compression work and expansion work. So this one is expansion work, and this one is compression work. And the difference of them will give you the network. And it can also be obtained from the difference of the Q's, because as I already said that in a cycle, W net is equal to Q net. So if you calculate the Q net from the difference of the added heat and rejected heat, this is the heat addition at this location, and this is the heat rejection at the exhaust cycle. exhaust process. So as you can see, you get exactly the same thing. So it's just the difference of the internal energies. So if you rearrange this or that, you will see that they are equal to each other. By the definition of efficiency, efficiency is always output divided by input. And output here is the network, input is the heat provided to the system. So if you use the network here, this is W net divided by Q in, so this one is Q in, you find the efficiency as 1 minus U4 minus U1 divided by U3 minus U2. Up to now, we analyzed a cycle that used air standard. According to the air standard cycle, we have to use the air table and read the values of the internal energies from the air table. On the other hand, if we assume cold air standard, in which the specific heat is constant, then calculations are a lot easier because we use the isentropic relations for cold air standard in which C is constant. So these are the isentropic relations, isentropic compression and isentropic expansion. And the same thing can be done from for the air standard, in which we have to use the air table. So here we need to get values from air table for isentropic cases. So this one is for air standard, in which we assume that specific heats are variable, so that we have to use air table. And this is the compression, and this one is the expansion. Whereas if we assume that the processes are cold air standard, in which C is constant, the specific heat is constant, then for compression and expansion, we can use these relations. In both cases, of course, we assume that compression and expansion are isentropic. So this is the isentropic compression for air standard, isentropic compression for cold air standard, isentropic expansion for air standard, and isentropic expansion for cold air standard. This is much more realistic than that, because with the assumption that the specific heat is constant, there is going to be some error in the calculation of the work output, efficiency, and so forth. And that's why the air standard, in which you use the air tables by assuming that the specific heat is variable, then you will get more realistic values than cold air standard. So for cold air standard, if you replace the internal energies by CV times T, because internal energy can be written as CV times T, if CV is constant, then the efficiency will be just 1 minus T1 over T2, or 1 minus 1 over R over K minus 1. Of course, the temperatures must be Kelvin. Remember this. R is the compression ratio, which is Vmax over Vmin, which is Vmax over Vmin. And K is the ratio of the specific heat, which is Cp over Cv. Its value is about 1.4. You can use 1.4 for most of the cases. And if you use this value, you're going to obtain an efficiency for cold air standard analysis, which is greater than the air standard, because this is not this is not as realistic as the air standard cycle. If you take a look at the variation of efficiency of the system with respect to compression ratio, you will see that as the compression ratio is increased, then efficiency increases also. Even though it seems that we can increase the compression ratio almost infinitely, there are some limits to it. First of all, mechanical limits. The strength of the material will not allow us to increase the pressure infinitely. This is one thing. Another thing is called knock or auto ignition, because for gasoline engines, if the compression ratio is very high, then the mixture will auto ignite. So before the spark plug ignites the mixture, it's possible that the mixture would auto ignite because the temperature inside is very high. That's why there is a limit to the compression ratio for the gasoline engines, and this limit is about 9. So most of the time, the gasoline engines will have a compression ratio of 9, and it's limited by this amount because of the requirement of the materials, as well as the knock phenomenon, which is auto ignition of the fuel due to the very high temperature at the end of the compression process. However, the auto ignition or knock process can be delayed by adding some fuel additives. In the past, one of the fuel additives was tetraethylate. In the past, they were adding tetraethylate inside the gasoline, which was delaying the knock process, so that the compression ratio was higher than 9. Then, because of the environmental effects of the lead, it's not used anymore. Instead, some other additives are used inside the fuel, such as uh, some kinds of alcohols, ethyl alcohol or methyl alcohol. Ethyl alcohol and methyl alcohol also delays the auto ignition, and it can be possible to obtain higher compression ratios by uh, putting some additives inside the gasoline. So typically, uh, gasoline engines can have compression ratios between 12 to 20, depending on the engine design. But normally, without any fuel additive, it's limited to 9 because of the material and knock conditions. Of course, this cannot be exceeded because of the especially material conditions. Do you have any questions up to now regarding the construction of internal combustion engine, reciprocating engine, and the Otto engine in particular? Any questions? Okay, so we can continue. There's a numerical example regarding the analysis of a Otto cycle, or in other words, spark ignition engine, or in other words, gasoline engine. We have four processes. You can see them in PV diagram. First, the air is compressed from the bottom center to top center so that its pressure is increased. Then at this process, heat addition takes place. So here we have compression work done on the system, heat added to the system. Then from 3 to 4, we have expansion work. So this one is WC, this one is WE, and the net of the expansion work and compression work is net work. Then we have to cool the gases, which represents the exhaust of the gases. So we have Q in, Q out, WC, and WE. Actually, the net work is equal to net of the works. So W exhaust expansion minus W compression, which is net work, is also equal to Q in minus Q out, because it's a cycle. We can see a similar graph, which is the TS graph. As you can see, the compression is isentropic, meaning that the entropy does not change. Then we have heat addition. Then expansion is also isentropic. Then we have heat removal. In the beginning of the cycle, we have atmospheric pressure, which is normal. The volume of the cylinder is 566 cubic centimeter. For instance, if you have a 4-cylinder engine, then it's going to be almost, I think, 2.2 liters. If there are 4 cylinders, the total volume of the cylinders is going to be 2.2 liters. The inlet temperature is 300, which is also typical because it's 27 Celsius. And the maximum temperature at the end of the heat addition process is 200 Kelvin. The problem is given with IP units. I have the solution in SI units. So let's take a look at some other data. The compression ratio is 8. So R, which is Vmax over Vmin, Vmax over Vmin, is given as 8. And if you look at the PV diagram, this one is the maximum volume. So V1 and V2, V1 and V4 is equal to Vmax. So Vmax is actually the volume at V1 and V4. And the minimum volume is when the piston is at the top center, which means V2 and V3 are equal, which are minimum values. So minimum value is equal to V2, which is equal to V3. So you can calculate or relate the compression ratio to the volume of the cylinder. It has given you the cylinder volume, the P1 pressure, T1 temperature, and the highest temperature inside the cycle. So let's take a look at the solution here, because at the end I have the SI solution. What is important is to uh, take a look at the solution. So from T1, which is given you as 300 Kelvin, you will go to the air table. So from T1, you can find U1 and VR1. VR1 is the relative pressure. And when you have VR1, because 1 to 2 is isentropic, 1 to 2 is isentropic, so that we have the relationship of VR1 over VR2 being equal to V1 over V2. This can be used for isentropic processes. So once we have this VR value from the table, then because we already know V1 over V2, which is actually the compression ratio, so this one is compression ratio, then we can calculate VR2. So once we have VR1, we can calculate VR2. From VR2, we go to the table and find T2 and U2 from table. T2 and U2 from table. So from table also, we can use the ideal gas law for calculating the pressure, because according to ideal gas equation, we have P1 V1 is equal to MRT1, and also we have P2 V2. M does not change, it's a closed system. So if you divide this from both sides, you obtain an equation which is P2, the pressure at the state 2 is P1 times T2 divided by T1 times V1 divided by V2, and it's obtained from the division of the two equations to each other. So you can obtain the pressure from this calculation. Then once you have the pressure at the end of the compression, you can move to the state 3, because the state 3 is state 2 to state 3 is under constant volume. When the volumes are constant, and if you divide them, volumes will cancel each other. So when the volumes are constant, from 2 to 3, you have only the relationship between the pressures and temperatures, whereas you have to include also the changes here, a change of the volume here. Here, V is constant. That's why you have this. Here, you need to divide the two equations of the ideal gas equations. And because the maximum temperature in the cycle is given, you can go to the table again and find U3 and VR3. So this is given from the table, you get U3 and VR3. And for the same reason as we mentioned in the first isentropic process, the expansion is also an isentropic process, so that the ratio of the relative pressures are equal to the uh, ratio of the relative volumes are equal to the ratio of the actual volumes. So this will give you VR4. From VR4, you can calculate, you can go to the table and find U4 and T4. So up to now, you have already all the internal energies so that you can calculate the works uh, of the compression, work of the expansion, the heat addition, the heat removal, as well as the uh, efficiency of the system. So by using the efficiency equation, the efficiency equation is 1 minus Q1 divided by Q41, which is the heat removed from the system, heat rejected from the system, divided by Q23, which is the heat added to the system. This is actually the same as W in W net divided by Q in. So this is actually the same thing as W net divided by Q in. So you obtain an efficiency of 51%. And we would like to calculate the actual work, because the work here is per unit mass of the air. So first we can calculate the mass of the air inside the cylinder by using the ideal gas equation. And we obtain the mass of the air, so that the actual work per cycle is obtained as m dot times work per unit uh, kilogram. This is work per unit kilogram times m, the mass of the gas, will give you the total work per cycle. And the total work per cycle is found as BTU. I have the solution as SI system. So you have everything in SI here. The inlet temperature is 300. The inlet pressure is 1 atmosphere. The maximum temperature, which is the temperature at the end of the combustion process or heat addition, is 200. The volume of the cylinder is 0.566 liters. The U1 value, which is obtained from T1, this is from table, air table. And once you have VR1, you can calculate VR2, you can calculate also the VR values at T1 and T2. So this is the VR value at T1, and this is the VR value at, it's written as VR2, but it should be VR2. It's written wrong. So VR2 is calculated from VR1. Then once you have the VR2, you go to the table again and read the value of U2 and VR3. So once you have the values of the U2 and U2 and VR3, you can calculate the P2 and P3 as I already explained in the solution. Then by using the ratio of the relative volumes being equal to ratio of the actual volumes, You can calculate V13, VR3, and T3. These are the table values again. And also, these are the table values. P3 is calculated as 3.48 atmospheres, as was obtained from the IP solution. This is the efficiency. Efficiency is the same, which must be the same in 2-unit systems. Mass of the air is almost 0.6 grams, and work done is 0.4 kilojoules per. This is actually kilojoules per cycle, so we have to put it as kilojoules per cycle. So if the engine is running at so many cycles per second, then you can calculate the power of the engine. So if you have, let's say, N is equal to 50 cycles per second, just as an example, then you can calculate the power of this engine as 50 times 0.4, which is 20 kilowatts. And of course, this is for one cylinder. If you have 4 cylinders, it's going to be 80 kilowatts for the whole engine. Any questions? Okay, we will have a break of 10 minutes and we will be back at 2. Here, we will analyze now the air standard diesel cycle. But let's first remember the difference between the diesel cycle and Otto cycle, or in other words, gasoline cycle. In gasoline cycle, we have a mixture of fuel and air at the beginning of the compression cycle. So we have a mixture of air and fuel here, and this air and fuel is compressed together. At this location, at this state 2, at the end of the compression process, the spark plug is energized and the mixture is ignited. The combustion is so fast that it takes place in a very short time, in which the volume remains the same. So that's why the combustion in the diesel in the Otto engine, in Otto cycle, takes place in constant volume. On the other hand, in diesel engines, at the beginning of the compression cycle, we have air only. So this one, the gas inside the cylinder at state 1 is air only, and air only is compressed. At the end of the compression cycle process, fuel is injected into the air, which is already at a very high temperature and pressure. And because of the high temperature of the gas, air, when fuel is injected, it starts to burn by creating higher pressure. But meanwhile, because the piston is moving down, the pressure does not increase. So this is where the combustion takes place in a diesel engine, which means combustion in a diesel engine takes place in constant pressure. So it's different from the gasoline engine. In gasoline engine, the combustion takes place in constant volume, whereas in the diesel engine, it takes place in constant volume. So as the injection of the fuel continues here, also the combustion continues, then it means that we have two types of work production. Here, when the combustion takes place, and here, when the isentropic expansion takes place. So the summation of them is the summation of the total work. So we have some work from 2 to 3, and the rest of the work is obtained from uh, 3 to 4. And of course, for compression, we have to provide work, and this is the exhaust work, exhaust heat, sorry. And here you see the TS diagram of the diesel cycle. The compression from 1 to 2 is isentropic. Then this is the heat addition from 2 to 3. Then isentropic expansion from 3 to 4. Then heat rejection. In the diesel cycle, we have, of course, the compression ratio, which is the maximum volume divided by the minimum volume. But we have an additional ratio, a volume ratio, which is called the cutoff ratio. The cutoff ratio is the volume ratio of V3 over V2. So not only do we have a compression ratio, which is V1 over V4 or V2. So compression ratio is V1 over V2. But we also have a cutoff ratio, RC, which is V3 over V2. So at the uh, expansion, start of expansion from 2 to 3, we have a constant pressure. And at the constant pressure, remember that in closed cycles, the work can be obtained by P times the difference of the volumes, because volume is constant. So this is part of the work. And actually, the heat added in the process can be obtained from the first law of thermodynamics, which is Q net minus W is equal to internal energy change. So from here, you can calculate the heat addition. And this was calculated up here. So heat addition is actually, if you do the calculation, it's du plus pdv, which you will remember as dH. So the heat addition in a diesel cycle can be obtained from the difference of the enthalpies. And this was, remember, in the Otto cycle, the difference of the internal energies, because it takes place in constant volume, but in diesel engines, the heat addition is obtained from the difference of the enthalpies. So we have the total heat transfer, Q23, which is the internal energy change plus this PdV, and you can see that it's just the difference of the enthalpies. Heat removal at the exhaust, and efficiency is always the network divided by the Q in. So the network is 1 minus the network is the WC, W expansion minus W compression, or it can be obtained from 1 minus Q out divided by Q in, which is actually the same as writing Q net, because Q net is just equal to W net. So instead of writing the efficiency as W net over Q in, you can write it as Q out minus Q in, Q in minus Q out, which is Q net divided by Q in. Then you can see that it's different from the efficiency of the Otto cycle, because in the efficiency of the Otto cycle, you had the difference of the internal energies, whereas you have the difference of the enthalpies here. In isentropic compression and expansion, you can use the table, air table. This is for compression, and also the same thing can be used for expansion because it's also isentropic. During the combustion, because pressures are the same, so you can calculate the temperature, because when the pressure are the same, P over, when the pressures are the same, you can relate the two temperatures to each other, which has only the change of the volumes. And you can also use the cutoff ratio to define the V over V3, because as you can see here, V over V3 is the ratio of the volume of 4 to the volume of 3, and we have already the cutoff ratio here. So by combining them, we can have a ratio of the V4 over V3, which has the compression ratio divided by the cutoff ratio. So up to now we have all the pressures and temperatures and internal energies as well as enthalpy for the combustion. If we use an air-cooled standard approach, then for the compression and expansion, you can use these relationships for cold air. And again, for cold air, you can calculate the efficiency by using this equation, and it's different from the efficiency equation for the cold air calculation of the Otto engine. If you look at the equation, if RC goes to 0, which means it becomes Otto, then you get the two efficiencies to be the same. You can prove this to yourself. It takes a little bit math. So when the cutoff ratio becomes 0, it becomes an Otto engine. Then in this case, you get exactly the same efficiency for the cycle. If we have Otto cycle and diesel cycle, sorry, this is not 0. I made a mistake here, so this was 1. So when cutoff ratio is 1, we get Otto cycle, and in this case, Otto cycle has the highest efficiency curve. Then for diesel cycles, for different cutoff ratios, you can see that efficiency curves behave differently. It means that at any compression ratio, the Otto cycle has higher efficiency than diesel cycle. So if you choose, for instance, a compression ratio of 15, a diesel cycle of cutoff ratio 3 is going to have a efficiency of 52, 53, whatever, but another diesel with a cutoff ratio of 3 is going to have almost 60%, and the same compression ratio found in this Otto cycle is going to have a efficiency of 65%. This example is related to an air standard diesel cycle in which we have to use the air table. Do you have any questions regarding the diesel cycle? The differences of the diesel cycle from the Otto cycle? Is it clear for all of you? Okay. In this diesel cycle, the compression ratio R is 18. The cutoff ratio is 2. The inlet pressure is 0.1 megapascal, which means it's atmospheric. Then we would like an inlet temperature is 300, a typical temperature. We need to find the temperature and pressure at the end of each process. So we're going to find T1, T2, P2, T3, P3, T4, P4, and T5, P5. Then we will calculate the thermal efficiency of the system, which is W net divided by Qin. Then we're going to find the mean effective pressure of the system, which is W net divided by the displacement volume. And as you can see, V1 over V2, which is the compression ratio, is given as 18. V3 over V2 is the cutoff ratio, given as 2. The inlet pressure is 0.1 megapascal, which is the atmospheric pressure, and inlet temperature is a typical temperature, 27 Celsius or 300 Kelvin. So now that this is a diesel system, we need to use diesel system for air standard. We need to use the air table. We are given T1, so we need to go to the air table. From T1, we will read the values of U1 and VR1. So we will read U1 and VR1. Once we have the VR1, because in the compression cycle, compression process, it's an isentropic process, we can find the values VR2 from V2 over V1, because it's an isentropic compression. And once we find the VR2, we can find the temperature 2 and U2. So these are the temperature and internal energies at the end of the compression process. Meanwhile, we can also calculate the pressure at the state 2 at the end of the compression pressure. And in constant pressure, remember that in combustion, the pressure was constant. When the pressure is constant, the temperature and volume can be related to each other like this, because if the pressure is constant, if you divide the two ideal gas equations with each other, the pressures will cancel so that the temperatures can be written in terms of volumes and the volumes and other temperatures. So we find that the other temperature to be the temperature at the end of the combustion to be 1796 or 97. So from this temperature, we go to the air table again. So from T3, we go to the air table, and from air table, we read H3 as well as VR3. Because from 3 to 4, we have isentropic expansion. Then in the isentropic expansion, we can use the isentropic expansion for the air standard gases. Then by using the cutoff ratio also, we can find the VR4. From the VR4, we go to the table again, and this time we read the values of T4 and U4. Up to now, we already have all the temperatures, pressures, and necessary internal energies and enthalpies. So by using the values, we calculate first efficiency. Efficiency is the network divided by Q in, or instead of writing network, we can write one Q in minus Q out. So Q in minus Q out is the net Q divided by Q in. Then it gives you this part. And as you can remember, the Q4 minus the heat rejected is found from the difference of the internal energies, because here V is constant. However, heat addition is obtained from the difference of the enthalpies, because here P is constant. Then we find the efficiency of the system to be 57 or 58%. Mean effective pressure is the cycle work divided by the displacement volume. And first, we can calculate the cycle work from the net Q, because network is equal to net Q. Then the cycle work is 618 kilojoules per kilogram. And the specific volume of the gas inside the cylinder at the beginning of the compression is found from the ideal gas equation. Is found to be 0.861 kilograms cubic meter per kilogram. So we can now calculate the mean effective pressure. And as you can see, mean effective pressure for this diesel engine is about 0.76 megapascals, or it's approximately 7.6 atmospheres, which is a typical mean effective pressure for a diesel engine. But of course, maximum pressure is much higher than this value. Let's check the maximum pressure, which occurs at P3 or P4. They are the same pressures. So this is, let's see, P3 and P4. I think it's not calculated, but you can calculate it easily by using the Yeah, P2 is equal to P3 because combustion takes place at constant pressure. And as you can see, it's 5.39 megapascals, which is 54 atmospheres, whereas the mean effective pressure is only 7.6 atmospheres. So there is a much large difference between the maximum pressure and mean effective pressure, and this is a typical mean effective pressure that you can find in a diesel engine. Additionally, I calculated the efficiency of the system by using the cold air standard. So if you assume that we can use cold air standard, then the efficiency of a diesel engine under the assumption of cold air standard, you use this equation, and this equation is going to give you an efficiency of 63%, and you can see that it's much higher than the efficiency of air standard. So this is much more realistic than that. Do you have any questions regarding the diesel engines, diesel cycle? So we finished the sections regarding the reciprocating engines, internal combustion engines. Now we will take a look at the gas turbines. Gas turbines are also internal combustion engines because combustion takes place inside the engine, but normally they are separated from uh, reciprocating engines, and that's why uh, usually reciprocating engines are only considered to be internal combustion engines, and gas turbines are considered separately. So in a gas turbine, which is an open system, so this is the most important difference between the reciprocating engine and the gas turbine. A reciprocating engine is a closed system, whereas a gas turbine is an open system. Remember, in open systems, mass can cross the boundary, whereas in closed systems, mass is constant. So no mass can cross the boundary in closed systems, whereas in open systems, it can cross the boundaries. Normally, a gas turbine has one compressor, one turbine, and one combustion chamber, and the shaft of the turbine is connected to compressor, and the other side of the shaft is connected to, for instance, a generator or the propeller of a ship. So as you can see, part of the work is transferred to the compressor, and part of the work is taken out as, for instance, generator work or propeller work, while heat is added at the combustion chamber. So this is where the fuel is burned, combusted, air comes in, it's compressed, fuel is injected into the air and combusted. The high temperature, high enthalpy gases rotates the turbine, and they are exhausted. During the rotation of the turbine, work is produced, and some part of the work is used to rotate the compressor. It's used for compressor, and some other part is used to obtain actual work, like generator work or the work necessary for the ship propeller. However, for analysis purposes, we can assume the system to be using the same uh, working fluid instead of uh, taking it from the atmosphere and rejecting the exhaust to the atmosphere. We can assume that the inlet and exhaust systems are connected to each other, and we use uh, air inside and heat addition takes place not only as combustion, but an external heat source adds heat into the system, and heat removal does not take place as exhaust of the gases, but it takes place as the heat rejection uh, at this heat exchanger. So here we have two heat exchangers, one compressor and one turbine, and it's used for the analysis of the actual system. Similar to the reciprocating systems, reciprocating engines, we can uh, still assume two approaches. One of them is air standard approach, for which we need to use the air table. The other is cold air standard, in which we assume that the specific heats are constant, and we do not have to use the air tables. So for the analysis purposes, as I said, instead of rejecting the exhaust out, we can recycle it. So according to this, in the top heat exchanger, which represents the combustion chamber, instead of combusting fuel, we add heat, which is Q in. And in the second heat exchanger, instead of exhausting any gas out, the gas is cooled. So we have Q out in the second heat exchanger. Then some of the work has to be added into the compressor, and we have a net heat and net work from the turbine, which is actually the total turbine work minus compressor work. So the net work is just turbine work minus compressor work. Such a system is called air standard Brayton cycle. So a gas turbine cycle which has one compressor, one heat exchanger for heat addition, one turbine, and another heat exchanger for heat removal that uses air as the working fluid is called air standard Brayton cycle. Because it's an open system, remember from the vapor cycle, we always use the differences of the enthalpies to calculate the works and heat addition and heat removal. Here also, because it's an open system, we will be using only the differences of the enthalpies for work calculations and heat calculations. The work necessary for the compressor is the difference of the enthalpies at the inlet of the compressor and the exit of the compressor. So we have 2 here at the exit of the compressor, 1 here. So H2 1 minus H1 is the compressor work per unit mass of the air. And turbine work is H4 minus H3. So this is the turbine work. Heat addition is H3 minus H2. So heat addition is H3 minus H2, and heat removal is H4 minus H1. By using them, we can construct the efficiency. Efficiency is always output divided by input. Output is the net work output. Input is the heat addition. And of course, we will be using the enthalpies this time instead of internal energies, as in the case of Otto engine. or partly internal energies, partly enthalpies, as in the case of diesel engine. Here we are using only the enthalpies. And of course, some part of the turbine work is used for compressor. It's called back work ratio. Back work ratio is the compressor work divided by turbine work. It means that so many percentage of the turbine work is used for compressor. And for gas turbines, it's usually between 40% and 80%. So it means that 40% to 80% of the turbine work is used to drive the compressor. It's a large value because it was only 1 or 2% for the vapor cycle. Remember that in order to run the pump, which pumps liquid from condenser to the boiler, it's necessary to use only 1 to 2% of the turbine work. However, in this case, it can be as high as 40% to 80%. In an ideal air standard Brayton cycle, you can see that we have 4 processes. In the compressor, the compression is isentropic, which you can see in the TS diagram. So compression takes place isentropically. Then heat addition takes place in constant. Heat addition takes place in constant pressure. So this is a constant pressure line. Then we have turbine work, which is the expansion inside the turbine, which is also isentropic, which means expansion takes place isentropically. Then heat removal in the second heat exchanger takes place in constant pressure as well. So here we have WC, Q in, W turbine, Q out. And as always, because it's an open system, the network is obtained from VDP, not PDV, because it's an open system, open cycle. In an open cycle, the network is calculated from VDP, not from PDV, and the net Q is always the integral under TS diagram. And of course, net Q and net W must be equal to each other because it's a cycle. In a cycle, Q net and W net must be the same because the initial and the final internal energies do not change. So if you write the conservation of energy equation, you will see that the delta U will be 0, meaning that the net Q must be equal to net W. And again, if you look at this graph, you can see that by increasing the compressor pressure ratio from 2 to 2 prime, it's possible to increase the work because the work is the area within this shape or within this shape. Because it's an air standard cycle, we will be using the air table. In compression, because it's an isentropic compression, we can use the air table. And for expansion, it's also isentropic expansion. We can still use the tables. If, on the other hand, we assume that it's an air standard cycle, the compression and expansion processes can be used by the relationship between temperatures and pressures. So in this case, you do not need to use the tables. You can just calculate the temperature at the end of the compression by just uh, performing this calculation, and the temperature at the end of the expansion by this calculation. However, if it's an air standard cycle for which you need to use the tables, then you have to go to the table to find out the PR values. Here we are using the PRs because we work with the pressures. We're not interested in compression ratio, which is the ratio of the volumes for the internal combustion engines. Here, when we say the compression ratio, we mean the compression ratio of the pressures. So one of the most important differences between the gas turbine analysis and internal combustion engine analysis, here we use the ratio of the pressures, whereas it was the ratio of the volumes in reciprocating engines. Now we are given a Brayton cycle. As you can see, this is a idealized Brayton cycle because there is no air inlet, there is no exhaust. Instead, to represent the inlet and exhaust, we have uh, replaced we have put a heat exchanger here to reject heat, which represents the exhaust process. And also, instead of a combustion chamber, we have another heat exchanger at which we add heat to represent the combustion heat. As you can see, in the compressor, we have an isentropic compression. So you can see that the entropy is the same. The heat addition takes place at constant pressure. So this is Q in. This was the WC, the compression work. Then expansion inside the turbine is also isentropic. So we have W turbine here. Then heat removal, heat rejection at the second heat exchanger also takes place at constant temperature, constant pressure, but it's a lower pressure than the pressure inside the upper heat exchanger. So we have basically two pressures, one high pressure at the exit of the compressor to the inlet of the turbine, another pressure, low pressure, the exit of the turbine to the inlet of the compressor. So we have two pressures in a gas turbine. So what we will do is to use the pressure ratios. So this pressure ratio is given as 10 in the problem. So maximum pressure P2 divided by P1 is given as 10. And because compression takes place isentropically, we can use the isentropic relations for air standard. We need to use the tables. So the first thing to do is to find the PR value and H value for state 1. So at the compressor inlet, we have T1. We go to the table. We read the values of H1 as well as PR1. So from PR1, we can calculate PR2. With PR2, we go to the table. We read T2 and H2. And from after we get T2 and H2, we can calculate PR3 during the expansion inside the turbine because it's an isentropic expansion. From we can find the PR4 by calculating the ratio of the pressures again. So from PR3, we go to the table and we read the values of T3 and H3. So up to now, we have all the pressures, temperatures, and enthalpies, meaning that we can now calculate the efficiency of the system. The efficiency of the system is W net divided by Qn. W net is the net of the compressor and turbine works. So we find the efficiency of 47%, 45% for this gas turbine. Now we can also calculate the backwork ratio. Backwork ratio is the compressor work divided by the turbine work. And as you can see, almost 40% of the compressor of the turbine work is used for the compressor. So only 60% can be used for useful work, such as rotating a turbine or rotating a propeller shaft. The cycle work is N dot. This is actually cycle power. N dot times the network. This is the network. And N dot can be calculated from the relationship of rho times AV, rho times AV. This is called volumetric flow rate, and it's given to you in the statement of the problem as cubic meter per second, so that you can calculate the mass flow rate into the compressor or into the turbine. It's the same mass flow rate. So by using it, you calculate the power of this gas turbine to be 2,481 kilowatts. So in the internal combustion engines, remember that by changing the compression ratio, the ratio of the volumes, it's possible to increase the efficiency, but there are some limits to it. For instance, for gasoline engines, the limit is auto ignition or knocking phenomena. In diesel engines, the limitation is material limitations. In gas turbines also, the efficiency can be obtained as a function of the pressure ratios. So the compressor pressure ratio, which is P2 over P1, as it's increased, as you can see, we have an increasing efficiency. The limit to the heat addition is because of the materials. So it says that due to the material properties, it's not possible to increase a temperature of 1,700 inside the combustion chamber or inside the upper heat exchanger. So as the maximum temperature taken to be constant, Tmax, let's say it's 1,800, the two different TS diagrams belong to two different pressure ratios. This one with a high pressure ratio, this one is a smaller pressure ratio. The cycle A, this is cycle A, has a higher pressure ratio, so its efficiency is higher. So efficiency A is greater than efficiency of B. On the other hand, if you look at the volumes under the graphs, you can see that the work of the B is greater than work of the A. So what it means is, even though the cycle A has greater efficiency, in order to have the same work output as cycle B, it has to be much larger. So during the design, it has to be taken into account whether the importance of higher efficiency or importance of higher work is more important. Any questions so far? Okay, we'll have another 10-minute break, then we'll be back at in the analysis, we assume that the processes are reversible, but in reality, this is not the case. For instance, the compression may not be isentropic because of the irreversibilities inside the compressor due to the friction of gas and moving components of the compressor. The entropy may increase. Also, inside the upper heat exchanger, we assume that the pressure is constant, but again, because of the friction, the pressure may drop. In turbine also, even though during the analysis we assume that the turbine is also isentropic, because of the friction of the gas and turbine components, the entropy may increase. And finally, in the bottom heat exchanger, there may be pressure change due to the friction of the fluid and the heat exchanger, or heat exchange may not take place ideally. But for this analysis, we're not going to take into account the changes in upper heat exchanger and lower heat exchanger. Instead, we will only take into account the irreversibilities in compressor and turbine. It's similar to the analysis in vapor cycle, vapor power cycle. So inside the compressor, we assume that there is an increase of the entropy because of the irreversibilities. Also, in the expansion process inside the turbine, there is also an increase of the entropy due to the irreversibilities as well. So when we take into account the irreversibilities, we use the concept of isentropic efficiency. Remember, isentropic efficiency for a turbine is the actual turbine work divided by the isentropic turbine work, because actual turbine work is less than the isentropic turbine work because of the irreversibilities. So we know that the actual turbine work is less than isentropic turbine work because of the irreversibilities. On the other hand, this is just the opposite in compressor, because we provide work to the compressor, so the actual compressor requires more work than the isentropic compressor. That's why the definitions of the isentropic efficiencies and of turbine and compressor are completely different. In isentropic efficiency of the turbine, we use actual divided by isentropic. On the other hand, the isentropic efficiency of the compressor is defined as isentropic divided by actual. So this is the difference between the two types of isentropic efficiencies. There's an example regarding this. A gas turbine has a irreversible compressor in which the compression does not take place isentropically, and an irreversible turbine in which expansion does not take place isentropically either. Their efficiencies are given as 80%. So both the turbine and compressor has an isentropic efficiency of 80%. Also, the other data is given as the same as the previous example. So we will be using the pressure ratio to be the previous one, which was 10. And temperatures and the pressures at the inlet of the compressors are the same. So the temperature is 300 at the inlet of the compressor. The air pressure is atmospheric. Because the compression ratio is 10, at the exit of the compressor it's 1000 kilopascals, and the maximum temperature in the system is given as 1400 Kelvin. So we're going to calculate the efficiency as well as other properties such as backwork ratio, the net turbine work, and so forth. And we're going to compare the two solutions to see the effect of the isentropic efficiencies on the system, overall system performance. So the thermal efficiency is always the net work divided by Q in. But in order to calculate the net work, we have to use the isentropic efficiencies this time. So both in the turbine and in the compressor, isentropic efficiencies must be included so that the actual turbine work is 565.5 instead of 706 for isentropic, and compressor work is now 349 instead of 279 for an isentropic compressor. So as you can see, the turbine produces less power because of the irreversibilities, and compressor requires more power because of the irreversibilities. So with the inclusion of the irreversibilities, we can now calculate the system performance. The compressor work is obtained from H2 minus H1. Remember this. So this is 1, 2, 3, 4. So in the compressor, you calculate the compressor work as H1, H2 minus H1. And of course, because you know the H1, you know the new compressor work because of the irreversibilities, you can now calculate the actual H2, which is the exit of the compressor. And you will see that the actual H2 is greater than the isentropic H2 because of the irreversibilities. So Q in can be calculated from H3 minus H2, H3 minus H2. And this time you will see that you have a much smaller efficiency of the system, almost 25%, and it was 30-something percent. So when you compare the efficiency of the system with irreversibilities is much lower than the previous system, which was reversible, which had reversible compressor and turbine. Similarly, if you calculate the backwork ratio is now 62%, and it was 40%. It's because of the irreversibilities in the compressor and the turbine, and because the turbine produces less work output and the compressor requires more work input, it requires that the backwork ratio is also higher than the previous one. It was originally 40%, now it's 62%. And also the produced power is much less than the original one. It was 2000 something kilowatt, now it's almost half of it. So by introducing only 80% of isentropic efficiencies, we have lost almost half of the power generated. So you can see the importance of the irreversibilities of turbine and the compressor must be appreciated. Any questions so far? So let's continue. At the exit of the turbine, we have to cool down the fluid, which means some energy must be lost to the surrounding. But this some part of the lost energy can be recycled, it can be recuperated by having a regeneration system or recuperation system. What happens is, instead of just rejecting the heat here, we can use a heat exchanger here, which utilizes the waste heat here to heat the air at the exit of the compressor, because the air at the exit of the compressor must be heated in the heat exchanger here. So if it's possible to add heat beforehand, it would be a requirement of less heat in this heat exchanger than otherwise. So recuperation system is just a system that uses the waste heat from the exit of the turbine. So as you can see, the compressor exit is heated by the turbine exit, and by doing this, we are saving some energy instead of just wasting it. So by using the recuperation system, regeneration system here, you can see that instead of heating the air from 2 to 4 inside the combustor, we get this part of heat as free because it's wasted. So normally, instead of heating it from 2 to 3, we use some of the heat, waste heat, as 2 to X, which is the heat taken here. So this heat is taken from this waste heat. And that's why it's necessary to put less heat here, which is normally H2 minus H3 minus H2. So normally in Qin, we had to put H3 minus H2. This is under normal conditions. But with the use of regenerator, now it becomes H3 minus HX. So the difference between HX and H2 is the saving. Of course, in this case, the exit of the turbine is not H4, but it's H2 because the heat is transferred to the other fluid, so it becomes Y at the exit of the regenerator. And this is the heat given from the regenerator. This is the heat taken from the gas at the exit of the compressor. Of course, the regenerator cannot transfer all the heat, all the waste heat to the first part of the cycle because in order to utilize all the waste heat, it's necessary to have an infinitely large surface heat exchanger, which is not so practical. Under normal conditions, a heat exchanger, a typical or practical heat exchanger, would have a surface area of a limited value. Then in this case, as the hot fluid, which is the exit of the turbine, is transferred to the cold fluid, which is the exit of the compressor. And as you can see, there is a temperature difference between the hot gas and cold gas. If it's possible to increase the surface area of the heat exchangers infinitely, then we will see that the temperatures of the hot fluid and cold fluid will approach to each other. At the limit, they will be the same. But this is not possible. This is not practical. So it means that we have to mention an effectiveness of regenerator or effectiveness of heat transfer, heat exchanger. So effectiveness of regenerator is H4 HX minus H2 divided by H4 minus H2. If HX and H4 are the same, then it means that the regenerator has 100% effectiveness. On the other hand, if HX, H2, and H2 are equal, it means that the regenerator has 0% effectiveness or there is no regenerator. So when there is no regenerator, H2 and HX are basically the same states, meaning that the effectiveness of the regenerator is 0. Otherwise, if it's possible to heat the exit of the compressor to the temperature of the exit of the turbine, then regenerator which would have an effectiveness of 100%, but it's not possible for practical reasons because in this case the surface area of the regenerator must be infinite. We have an example regarding the gas turbine with the regenerator. So in this gas turbine, actually the inlet conditions are the same as the previous ones. So we're going to see the difference, what happens if we use a regenerator in this gas turbine and how would the efficiency of the overall system would be affected by the addition of a regenerator. So this is a regenerator with an effectiveness of 80%. And because of the regenerator, the exit of the compressor is heated from 2 to X. So this heat comes free from the waste heat. So this can be called as a free heat. And it's obtained from the exit of the turbine, which cools down from 4 to Y. So this is the heat transferred to the compressor exit, the heat transferred to the compressor exit, and the regenerator effectiveness is 80%. We would like to find out the effect, the influence of the effect of the regenerator on the system performance. So we are now writing the equation of the regenerator. It's Hx minus H2 divided by H4 minus H4 minus H2. We are given the effectiveness of the regenerator so that we can calculate the enthalpy at the exit of the regenerator. So enthalpy at the exit of the regenerator is 762 kilojoules per kilogram. This is because of the using of the waste heat. So by this increased Hx, now we can calculate the new efficiency of the system. And new efficiency of the system is found to be 58%, which is much higher than the previous one. The previous one was, I believe, 30-something%. So as you can see, with using some of the waste heat, it's possible to increase the system performance or system efficiency. In the problem, it's also asking to plot the efficiency versus regenerator efficiency. It's not shown here, but I did it on Excel and I added a graph on the final page. And as you can see, when there was no regenerator, the efficiency was 37%. And with a regenerator of 80%, now the efficiency is 58%. And in between 0% effectiveness of the regenerator and 80% effectiveness of the regenerator, you can see that there is a substantial change in the efficiency of the system from 37% to 58%. So we gain almost 20% of efficiency by utilizing the waste heat. Any questions? Okay, I think you don't have any questions. Next week, we're going to have midterm exams, you remember, and not next week, the week following the next week. So I hope you're getting prepared for them. Professor, is our next lecture going to be online? Yeah, we will have, it's actually hybrid, which means I will be at the school. So while I will be in the classroom, I will be also using the remote teaching. It's called a hybrid system. If you can come to the classroom, you are most welcome, of course, because in the classroom it's much more effective than the remote teaching, distant teaching. So it's going to be hybrid. You can come to the classroom or you can be at home, as we did in the remote teaching. It depends on you. Any questions? So I'll see you next week then. I don't have any other material here. I'm stopping today's lecture if you don't have any questions. Okay, see you next week then. Bye.